Okay, so we're getting closer. If you're taking the OGT in June, then Amy should have sent out a little form to fill out, and you should know what days and times you're taking the tests now. If you haven't signed up to take the OGT yet, email or send Amy a text message, however you've been contacting her. If you don't know your testing date, get into contact with Amy and she can let you know. So today we're going to practice a few topics. We're going to talk about distance equals rate times time. We're going to talk about some probability and something called the counting principle. And then at the end, if we have time, we're going to talk about how to tackle those free response type problems. So we're starting out with distance equals rate times time. This is a formula that you need to have memorized. It will not be on your reference sheet. They give you area formulas and volume formulas. They do not give you this distance equals rate times time. They assume you know this formula. So an example problem you'll see with this is usually when you're doing some sort of travel problem. This is all about speed and time. So rate is just another word for speed. And it's something you might actually use when you're driving. If you're going 65 miles an hour and you've been traveling for 3 hours, you can figure out, well, how far will that take me? What's my distance going to be after 3 hours? So you'll know to use this formula when they give you this travel type problem. So the problem states the Johnsons were going to a family wedding and drove a total of 1,244 miles to reach their cousin's house. So they talk about driving to an event. That's how we know use this distance equals rate times time. They spent 9 hours driving the first day at an average speed of 60 miles per hour. They reached their cousin's house on the second day after driving 11 hours. So the question is, what was their average speed on the second day? That's highlighted. They even split it from the main question, so you know this is what they're actually asking. What's the speed on the second day? So we go to our first part of the problem where it says they spent 9 hours the first day at an average speed of 60 miles per hour. So for the first day, we're going to use this formula, distance equals rate times time. And we're going to plug in 9 and we're going to plug in 60. What letter are we going to replace with the 9? Where would the 9 hours go? Is it going to be the D, the R, or the T? Remember to answer, you can type in the chat box or you can unmute yourself. Thank you, Tasha. That will be T. So 9 goes in the T spot. So then the speed of 60 miles per hour, where will we place the 60? R. Good. So when we do that replacing, then we have to decide, what can I do now? Since the 60 and the 9 are on the same side, we're just going to multiply those together. 60 times 9 is 540. So on the first day, you would have traveled 540 miles. So now we go back to the question and we say, well, what's happening on the second day? On the second day, the only information they gave us was they drove 11 hours. So we've got to use some other information in the problem to find at least one more piece of this second day. So it said they drove a total of 1,244 miles. So we can use that to figure out, well, how many miles did we drive on the second day only? all this work for the first day told us on the first day we drove 540 miles only. So if we know the total of something and we know part of something, we can subtract those two numbers to find the other part. 1,244 minus 540 is 704. So on the second day only, they drove 704 miles. And it said it took them 11 hours. So we need to use that distance equals rate times time formula a second time. But this time we have new information. 704 miles, is that going to go in for D, R, or T? Is it your distance, your rate, or your time? Good, thank you, Kenya. 704 miles is the distance. It is D. So 11 hours, will that be rate or time? Where should we put the 11? R or T? Good, time. And usually you can tell by the units, hours means time. So this time our setup is different. First day, we just had 60 next to 90 and we multiplied. This time the 11 is on the completely opposite side of the 704. We need to do our opposite operations at this point because we want R to be alone. So if R is multiplying by 11, what opposite do we use to get the 11 over to the other side with the 704? What opposite should we use? Good, divide. We're going to divide that 11 over. So 704 divided by 11, I don't know what that is, so I'm going to hit up the calculator. Remember, you will have a little handheld calculator on the test itself. So you will have access to one when you take the exam. So 64, I was about to write 24 for some reason. 64 equals the rate. That was what we were looking for. On the second day, we traveled 64 miles per hour. So problems like this, they'll have a pretty similar setup every time, just needing to have that formula memorized and having to figure out what happened the first day, how's that going to affect my second day, and use that information to find something happening on the second day. So let's practice one more. Enrica took 2 days to drive 1,020 miles. On the first day, she drove 10 hours at an average speed of 62 miles per hour. On the second day, her average speed was 57 miles per hour. Approximately how long did she drive on the second day? So again, a very similar setup. They don't tell you the formula. You would need to know distance equals rate times time. So on the first day, I want you guys to use the information. She drove 10 hours at an average speed of 62 miles per hour. That was all our information from the first day. I want you guys to find what distance did she drive on the first day. So I'm going to give you a minute or two to find what distance did she drive on the first day. Okay, so we have one answer already, 620 miles. So she did drive 10 hours on the first day. That is also true. But we need to use that 10 hours to then find the distance. And Kenya is correct. The distance is 620 miles. Distance equals rate times time. The rate is 62 times the time of 10 hours. So multiplied together, that gives us a distance of 620 miles the first day. So we take the information given, use it to find distance. Now we need to find what distance did she drive the second day. This has to do with the total amount. The total was 1,020 miles. And then only on the first day was 620. So how can we use the total amount, 1,020, and the amount she drove the first day to figure out how much she drove the second day? What do we do with those two numbers? Or what is the distance she drove the second day? Either way. Okay, 400 the second day is correct. We find that by doing subtraction. If you have part of something and the total, subtract those two numbers. So now on our second day, we have a distance of 400. We just figured that out. And then they told us a speed of 57 miles per hour. So now we have to figure out the actual question. How long did she drive on the second day? We always go back to this distance equals rate times time. So this time, just like our first example problem, after we plug in the numbers, we're going to have to do some opposites. We don't just multiply together. So we've got to plug in for distance and plug in for speed, which is r, rate is the same as speed, and then solve for t. So what are you guys getting for the time? What do you get for the time she drove the second day? Good, 7 hours. If we plug in distance of 400, speed of 57, then we do our opposite of division. 400 divided by 57 is 7.01, which is approximately 7 hours. So those distance equals rate times time problems, again, they're pretty much the same setup every time that I've seen on all the practice tests online. But you do want, if you're making flashcards or however you're preparing notes and how you study, make sure you get this formula memorized. So the next topic is going to be the counting principle. And it's not, again, going to be called that. We knew the last problem was distance because someone was driving somewhere and they gave us a speed and a time. This one, they're not going to tell us use the counting principle. Usually it'll have the words how many combinations or how many options, something like that. And we'll use this thing called the counting principle. So let's look at the example and then I'll explain how we use this counting principle. Casey has one afternoon to run errands involving buying a sweater, mailing a package, and buying groceries. There are 3 clothing stores, 2 post offices, and 4 grocery stores within a 10-mile radius. How many combinations of 1 clothing store, 1 post office, and 1 grocery store are available within a 10-mile radius? So some of these numbers are extra that don't matter. Being within a 10-mile radius doesn't really matter so much for this type of problem. When we're picking how many options we can do, how many ways we could accomplish this, we just care how many different of our choices are there? So for the clothing stores, there are 3 different choices. I could go to clothing store 1, I could go to clothing store 2, or I could go to clothing store 3. Maybe one's closer to one of the other options. Whatever your reasoning, you can pick from those 3. So then option 2, there are 2 post offices. So for every clothing store you could pick, first you make a choice. Say you choose clothing store 1. Then you have a choice to make for the post office. You could pick post office 1, or you could pick post office 2. But instead, say you chose clothing store 2, you could have picked post office 1 or post office 2 after that. So see how it's getting bigger each time. Once you've made one choice, you then have to go on to your next choice, and it kind of expands out. And then for grocery stores, you could go to grocery store 1, grocery store 2, grocery store 3, grocery store 4 for each of your other choices. So you could write out this kind of table or chart that I'm making, but that is very time consuming. These tests are timed, so it's easier to just use the counting principle. And the counting principle states that instead of having to write it out all like this, you can just multiply your options together. 3 times 2 times 4. It's a lot of explanation for a super simple process. Multiply these together. It's just remembering I can use this process of multiplying them together to get my final answer. And always just use your calculator. It's easier to not make mistakes if you're typing it in and you can look back. So 3 times 2 times 4, 24 total choices. So again, those keywords to know, I just can need to multiply these together, are how many combinations or how many ways. It'll be something like that of how can you pick to do these things. Okay. So let's practice another problem of this. One style of jacket comes in 3 sizes, small, medium, or large. These jackets have either buttons or zippers. The jackets are available in 5 different colors. So you just need to identify what are my options that I'm choosing from. We had sizes. Sizes are your first option to choose from. And then buttons or zippers, I'm going to call that how you close the jacket. And then colors was your third option. So once you have the numbers for those 3 things, you just multiply them together. Most of the time they just tell you, but sometimes they list out the things and you have to count up. So how many sizes did they tell you there were? How many size options were there? 3. Okay. How many ways to close the jacket did they tell you? 2. So this one, they didn't ever say the number 2. They just gave you 2 options, buttons, zipper. And then how many colors? 5. Good. Once you do that, multiply it together. So what's our final choice for this one? 30. Good. 3 times 2 times 5 gives you 30. So again, these questions pretty straightforward. If you know, I just need to multiply these numbers together. Okay. So next we're going to talk about probability. Probability, you'll see usually a couple questions of probability. Counting principle, you'd probably only see like 1 question on the test. Same thing with distance equals rate times time. Probably 1, maybe 2 questions of that. If their tests still match what they have online. I've been basing this all off what they've provided online. So probability, you'll see a couple of them, and they'll usually ask them a couple of different ways. But it all comes back to the same concept. Probability is based off what you want to happen over the total ways it could happen. So for example, Leroy has a number cube, and they like using these number cube problems. If you're not sure what that means, that's just a die or a dice. It's the six-sided. It depends on if you like playing board games or not, probably, as to whether you see dice at all. So it has numbers 1 through 6. You roll it, one of the sides will show up. So that's what they mean by the word number cube. So with sides labeled 1 through 6, he tosses the number cube 4 times. Each toss results in a 5. What is the likelihood that the next toss will result in a 5? So they're trying to be a little bit tricky here because they listed all the other tosses. If they don't keep an entire chart and say base your answer off this chart, they would use the words like experimental probability. This doesn't actually matter. This whole sentence and this whole sentence don't affect what's going to happen. When they ask the likelihood, which is just another word for probability. So when they ask the probability, we're basing it solely off the number cube itself. So what's the probability the next toss will result in a 5? This is what we want. We want a 5 to come up. So we look at our object or our situation and say, well, how many ways could that happen? On this number cube, how many of the sides are a 5? Just one of the sides. A lot of people want to use that 5 and say maybe 5 out of 6, but only one of the sides is actually the number 5. So what we want is only going to happen one way. So then how many total sides does the number cube have? 6. So total is 6. Sometimes we have to reduce or change this answer, but a lot of the times that's just it. Once we've identified that, that is our final answer, 1 over 6. There's 1 out of 6 ways to roll a 5. So they can make it a little more complicated, but again, always go back to what do we want to happen over the total. No matter what else is going on, what we want to happen over the total ways it can. So this situation, Joel plays tic-tac-toe on his computer. The computer plays first and randomly places an X in one of the grid squares as labeled in the diagram. So somewhere we'd have an X placed when the computer makes his move. The frequency table shows the computer's first move for 50 games. So it gives us a table, says the first move for letter A, the computer did 5 times, or for letter B was 3 times. So he just tracked every time he played, this is what happened. Based on these results, what is the experimental probability? Even though they're using the word experimental, we still do want over total. We're just going to base it off this table instead of, like on the last example, we just knew on a number cube, this is what happens every time. So experimental probability that the computer will place an X in a corner square on the first move of its next game. So they said in a corner square. What we want is a corner square. So what letters are the corner squares on our grid? A, C, G, and I. Good. So here are our corner squares. So now this is where the table comes into play. We need to use the numbers for each of those letters and find all the ways it could happen. So with A, C, G, and I, how many total times did the computer pick A, C, G, or I? So still not seeing an answer yet. So let me give a hint. So we have our numbers that go with A, C, G, and I. All we need to do to find the total amount, all the times the computer picked it, is to add them together. If we add all those numbers for A, C, G, and I together, then we can find how many times it happened for what we want to happen. Good, 26. And we did just have someone join. Thanks for joining. Can you hear me, Carrie? I just want to double check on that before we get too far forward. I'll type a message too, just in case. While I wait on a response for her, let's talk about the total. So the total would either be all of them added together, or they often just tell you. They said he tracked it for 50 games. They say it in 2 spots, that that's the total number of times he did it. Okay, so let me respond to Carrie. So once you know the answer, 26 over 50, you may need to reduce. Our last one, 1 over 6, didn't reduce at all. 26 over 50 can reduce. When we reduce a fraction, we look for any number that divides into both the top and the bottom. So for the 26 and the 50, what's one number that would divide into 26 and also into 50? And while people are thinking about that, I'm just going to try and catch Carrie up. We're talking about probability right now. Probability is always based off what you want to happen over the total ways something could happen. This problem asked us to find where a computer would place a corner square, and they told us the corner squares are A, C, G, and I. So we added all those numbers together. 5 plus 8 plus 6 plus 7 gave us the 26. So that's what we wanted to happen, and the total ways it could happen was 50. So now we're trying to reduce this fraction, but we need to know one number that divides into both 26 and also into 50. Here's another hint. They're both even. One ends in a 6, one ends in a 0. Even numbers can always divide by the smallest even number. What's the smallest even number possible? Smallest positive even number? 2. A lot of the times it'll be 2 or it'll be 3. So 2 divides into 26 and into 50. We plug those into a calculator. 26 divided by 2 is 13. So that's the top half. And 50 divided by 2 is 25. Now, Sometimes you have to reduce more than once, so you can check again to see if there's any number that divides into 13 or 25. So another method to check is just to take your calculator and try numbers. Say, well, I'm not sure what divides into 13. 13 divided by 2 is 6.5. That did not divide in. We don't want a decimal. So then I'm going to just try one more number up. 13 divided by 3. Nope, still a decimal. 13 divided by 4. Still a decimal. And you can try it a couple of times. If you keep trying it and every option you try is a decimal, then you can be pretty sure there is no number that divides into 13. So that means this is as reduced as it possibly can be. 13 over 25 would be the final answer. So still some probability. This time I want to show you how they can write the answer a couple of different ways. We still are focused on probability. We're still focused on want divided by total. But all the answers so far we've seen have been fractions. They can actually show it a couple of different ways. So this problem says Drake's school awarded 450 raffle tickets as incentives. The principal will draw one winning ticket. The winner will receive a CD player. We didn't really need to know that for the problem. It doesn't help us solve the problem. Drake received 3 tickets for good attendance, 5 for making the honor roll, and 2 for tutoring other students. What is the probability that one of Drake's tickets will be selected by the principal? So, how many tickets did Drake have? We want Drake to be the winner. So what we want is how many tickets Drake has. What's his total number of tickets? Good. 10 tickets. They told you up here he got 3 and 5 and 2, and if you add those all together, 10. So then we need the total number of tickets. And this they just told you in the problem. What was our total number of tickets? Good, 450. So our first option is, good, both of you guys are correct. 450 is the total number. So our first option of how to write the answer was to reduce this fraction. Is there anything that divides into both 10 and into 450? Two works. Can anyone think of a bigger number? 2 does work, and it's definitely a great option. 10 is a bigger number. If you can think of the biggest number, it saves some work for you. By using 10, that means we only have to do this once instead of multiple times. So 10 divided by 10 is 1, and 450 divided by 10 is 45. So this could be the way they write the answer. 1 over 45 could be the final answer. They can also write it as a decimal. So if you get your fraction, 1 over 45, but the answers are as decimals, we know the fraction bar really means to divide. So here we definitely have to use our calculator. 1 divided by 45 will be a really weird decimal. 0.022222 forever. And they would tell you where to stop. If I said round to the nearest hundredth, what would that look like? Where would we stop if it says to round to the nearest hundredth? Good. 0.02. So that's option number 2. That could be our answer choice. Option number 3 is to write it as a percent. Once you get the decimal, you do need the decimal first in order to get the percent. We just multiply by 100. All percents are out of 100. So if we multiply by 100, (0.02 times 100 is 2. So 2% is the last way we could write the answer. So again, it's not that the concept of probability changes at all. We're always going to do want over total. But sometimes they give us a chart, and we have to interpret this chart in the correct way to find the probability. So I wanted to also do a problem like this because interpreting this chart can be kind of confusing. So the population of a certain high school is shown in the table below. So it breaks it down like freshmen. There are 165 female freshmen, or 138 male freshmen, or there's 303 total freshmen. So we can see that the entire table just has a lot of different information for every category we can think of at that school. So what is the probability that one student selected at random is both a senior and a female? And then I asked a second question down below. We're going to ignore that for now. So what number is representative of senior and female? Good. Yep, you guys are both correct. 159 is both senior and in the female column. So that's what we wanted. We wanted someone who is both senior and female. So then they said one student selected at random. They didn't limit us. They just said from all the students, we're selecting one. So what's the total if we're picking from all of the students possible? Good, 1,178. That can be a tough one because there's a couple of different totals, but we wanted the total of everyone. So they have this as a percent. So remember that to find it as a percent, we had to plug it into a calculator and then multiply by 100. So I want you guys to find the correct percent. If you divide that out and multiply by 100, what is the correct percent? Good. 13% is correct. And if we plug it in, 159 divided by 1178 times 100 gives us that 13. So I gave a second question just to show how it can be a little bit different. What is the probability that a male student selected is a sophomore? So they're really limiting us on this chart. They want the male students only. We don't care about the female column at all, which means the total column isn't going to help us either. Females are not involved in this particular question. So we need the number for a sophomore and the total number of male students only. We want the male sophomores and male total number of students. Good. 131 is the male sophomores and 564 is the total number of males. So just because they give us a total of everything doesn't mean that's always the total we want. With a big one like this, they're going to ask you as a decimal or fraction for the most part, as a decimal or a percent. Reducing this fraction would be kind of difficult. So most likely they'd either have it as, okay, good question, thanks for asking. How did we get 564? Male students, if we look at our chart of male students, then 564 lines up with the total number of male students. And since they limited us to male students only, we only wanted this total number of males. Does that make sense? Okay. Yep, there's a lot going on in this chart, so it's easy to miss all those little pieces. So finding the final answer, we do the 131 divided by 564, which is 23, or 0.23. And then we could times it by 100 to get the percentage of 23%. Good. So then one more question. Again, it always is going to go back to 1 over total. That doesn't change. But there's a little bit of variation on all of these. So this one, Michelle writes the letters for the word Mississippi on individual pieces of paper and places them in a bag. She randomly draws one letter, then places it back in the bag. Then she randomly draws a second letter. What is the probability that the first letter is S and the second letter is P? So they gave us 2 probabilities. They want us to find a probability 1 and a probability 2. When that happens and you find both probabilities, to get the final probability, you multiply them together. So even though we're still doing want over total for both of these, once you do that, we're going to have to multiply together to find the final probability. And that's how this is different. Since we have 2 of them, we have that extra step of multiplication. So the first probability, the first letter is S. We want to go over to Mississippi, and they're saying each of these is their own card. So we want to count how many S's are in the word Mississippi. Good. 4 S's. So then we just need to know the total number of letters in Mississippi. Good. Always double check your count, especially with a lot going on. It can be easy to miscount. So try counting twice just to be safe, but there are 11. So there's one other key thing it says in here. So she draws one letter and then places it back in the bag. That's super important. There's two types. There's one where you put it back in or one where you leave it out, and that actually affects the total. If we put it back in, we still have a total of 11. But if we picked one and then left it out, we would only have 10 letters left. So you have to watch for those words to know how it's going to affect that bottom number. So then she randomly draws a P. So for the second one, we're looking for the letter P, and someone's ahead of the game, already counted it up, and we know there is 2 letter P's with our total still of 11. So when we plug this into a calculator, we use the divide sign. 4 divided by 11 multiplied by 2 divided by 11. And you can just type in the whole thing. If it's all divide and multiply signs, just type the whole thing in at once. So this time it said to round to the nearest 10,000th, which is 4 spots, 0.661. But they also had answer choices here, so you knew how much to go to. So that pretty much covers probability. Like I said, they'll have probably 2 to 4 questions, maybe 3 to 4 probability questions. Usually you see it a couple of times, at least from what I've seen with the online tests. So then the last problem I wanted to talk about today was just one of these free response where you have to write your answers out. You got to show your work and explain what's going on. You're not just picking an answer. So one thing that you see a lot, and we have had one session on it, I'm probably going to talk about patterns again because it happens so much, is finding these patterns. You'll see a couple of questions on the test with patterns. So a pattern of shaded and unshaded squares is shown below, and it gives us our figures. In your answer document, find a formula for or describe in words. So they give you 2 options. Find a formula or describe in words the number of shaded squares in the nth figure. So when they say the nth figure, that means any figure you want. If you wanted to know the 100th figure or the 500th figure, the nth figure is, I want to describe this for any figure I want to know about. So, and specifically they said the shaded squares. So for figure 1, how many shaded squares do we have? Just 1. How about figure 2? 3. Good. So figure 3, 4, and 5. What comes next? Figure 3 does have 5. Figure 4, how many shaded squares in figure 4? 7. And how many shaded squares in figure 5? 9. So we want to look for a pattern. Do we notice anything in common about these numbers or anything they're going up by every time? What's special about this? So one thing that's special is you're adding 2 every time. Okay, so one way we could describe this is we're going to add 2 to the previous figure. We added 2 to figure 4, and that gave us figure 5. So you could write a sentence something like this. To find the nth figure, you add 2 to the previous figure. That should be one acceptable way to write your answer. Any other things you notice about this? 1, 3, 5, 7, 9, they're all a special kind of number. What would we call these numbers when they're all good? They're all odd numbers. So a second way to write this, to find the nth figure, you find the nth odd number. There's usually multiple ways to answer this correctly. Okay. So the last way would be to find a formula. Formulas can be difficult. If it's a linear pattern, that's the easiest formula to find. So since it is linear, and how do you know that it's linear? When you add the same thing every time, that means it's linear. So if it went add 2, add 3, add 5, add 8, whatever pattern it was, that's not linear because you're not adding the same thing every time. Or if it was multiply by 2, not linear. But since this is linear, we could actually find the formula. And it's not so bad to find this formula if you have the setup memorized. So for a linear formula, it is the amount of change. That's our plus 2 we have here every time. Multiplied by, usually we just say x, whatever variable we want to use. In this case, they did say the nth figure. So our amount of change, we're going to say times n in this case, because they told us to use the letter n, plus the starting amount. So that's another good thing to have memorized. And it is very generic. I don't like to get too specific with it because there's a lot of different ways they can present this, so it's good to have this kind of generic setup memorized. So the amount of change, we already have a number. What's our amount of change every time? Add 2, so we have 2n, or 2 times n. Sorry, getting kind of squished here. I'm gonna write it down here, 2 times n. So the starting amount can be a little bit trickier. Starting amount would be if we went back and had a figure 0. Starting amount is not 1, it's actually 0. So we have to go backwards. If we went back a figure, what number would we be at? So when we went forwards, we added 2. If we go backwards, we're going to minus 2. So subtract 2, but we want to actually find the amount. So we want to do 1 minus 2 to get back to the actual number. We don't want the amount we're changing by going backwards. We want the actual number. So what do we get if we do 1, subtract that 2? -1. Good. So the starting amount is -1. And sometimes the starting amount doesn't make sense. You always want to do it based off the pattern and not just based off, if we physically were making this, we can't have -1 blocks. But we've got to base it off of the pattern we found. So you guys are both correct. -1 is that starting amount. So then you could say to find the nth figure, use the formula 2n minus 1. So 3 different ways that should still answer that first part of the question. So then there's usually more than one part. And when you're writing this out, I think it's helpful to write out this table too. I think you'll still get points for being very specific and showing what happens with each figure. So then find the number of shaded squares in the 50th figure. Excuse me. Show your work or explain your answer. So show your work, that works better if you did find the formula. Again, we had a couple ways to answer that first one. So we'll talk about the first 2 in a second. For the formula, that just means plug it in. 2 times 50 minus 1. Now I might label that you're finding the 50th figure. You could say equals or put a semicolon or a colon to say what comes next is the 50th figure. And then you just simplify this. What do we get if we do 2 times 50 minus 1? Good. 99 is correct. Okay. So what if you didn't find the formula? Because having those first 2 answers, just as good of a way to do it. Well, if you didn't find the formula, it does make it harder to find the 50th figure. I'm going to have to go to a new page. I ran out of room. So to find the 50th figure, you might have to actually just write out the pattern over and over again. Without the formula, all we know is we keep adding 2 every time. So we were up to 9, we would just keep going, adding 2 every time. 15, 17, and 19. But you can kind of find a secondary pattern eventually to make it so you don't have to write this out 50 times. It is a pain in the butt if you don't have the formula because you're doing a lot of writing it out. 19, 20. So let's see. 19, add 2 is 21, 23, 25, 27, 29, 31, 33, 35, 37, 39. And I'm probably not being good enough labeling my tables. Just to make sure it's a little clearer, this was just the figure number 1, figure number 2, and this was the number of shaded squares. Running out of time, so I was getting a little bit lazy and I didn't write that out, but that can be confusing. So figure number 10 was 19 squares, or figure number 20 was 39 squares. So there's a little pattern there that you can follow that means we don't have to write this out 50 times. If figure number 10 gave us 19 squares and figure number 20 gave us 39, what do you think figure number 30 should give us? What are we adding to get from 19 up to 39? And what do we get when we add it again? close. 19 to 39 is add 20. 49 would be if we only added 10 more. But we actually went up by 20. 19 to 39 takes us up 20 spaces or blocks. So if we add 20 again, it takes us up to 59. So if we do that again, if we go up to 40, we would go 20 more again. So how many blocks would we have with 40? 79. And so then one last time, we already know it's going to take us up to 99 because we found that answer with the formula. But if we're writing it out, it takes us up to 99. So if you don't see that secondary pattern, you can always just keep writing it out. You could just go 21, 22, 23, 24. So you can write it out to find the answer. It's just a little time consuming, but it will still get you full points. If you write this entire table out and get to 99 as your 50th block, you'll still get full points on that. So we're out of time for today. Again, OGTs are coming up. Make sure you know your testing time. If you're not sure, talk to Amy, the coordinator, Amy Wright. And if you don't know how to contact her, send me a Remind 101 message and I'll give you that information. So have a great day, everyone, and thanks for joining.